So let's do a couple examples of the goodness of fit test. So here's our M&M example again with the same percentages. And now we are going to take a sample of 400 M&Ms from the M&Ms that the M&M company makes. So what we find is this was given to us. The frequency for each of the different colors of the 400 M&Ms is given. And the key thing to see is that is your observed. So they took the 400 M&Ms and they just looked at how many of each color were there. So that was the observed because all they did was observe it. Now, when we talk about expected, which is obviously what it says over here as well on the left-hand side, but the expected would be if we took a sample of 400 M&Ms and they had the percentages that the M&M company claims, how many should be those different colors. So in order to find expected in this case, we do just N times PI, and all that means is just it's the number of M&Ms times the percentage that is in the claim distribution. So we would do something like this. And it looks like this will give us 92. And then, you can write this, but this is the same exact one. So for orange is the same. And if you want, you can pause and come up with the other values. But each one is simply that 400 times how many, the percentage of how many should be in there. So 0.15, and red is 0.12. and yellow is another 0.15, and brown is 0.12. So we have a lot of the same numbers here. So we'll have 60 and 48 and 60 and 48. And then what the goodness of fit test does is it looks and says, okay, how far apart is 80 from 92? And how far apart is 75 from 92? And how far apart is 40 from 60? And you're trying to see, is there significant evidence here to support the claim that it's different, or depending on the claim, do we have sufficient sample evidence to reject the null hypothesis, which is that it is what they say it is. So now we have these numbers, we have everything we need. So is the proportion of each color different than the claim of the M&M's manufacturer? So understand that the claim is that it follows that distribution that you see up there. So we've already written this down. We actually wrote it down on one of our first pages, but it's simply that the probability or percentage of blue, or proportion, however you want to say it, is 0.23, and for orange is also 0.23. So I'm writing out all the different proportions here along with what the M&M's company claims. So P, we did, that was green, we have red, we have yellow, we have brown. Okay. And then remember from earlier that the alternative hypothesis is simply at least one of the probabilities is different. Okay. And so I do not have M&Ms, but just to kind of show you the idea here, this is some trail mix. And the idea is just like this trail mix has nuts and it has chocolate and it has like berries, and there's a certain percentage that are nuts and there's a certain percentage that is chocolate and there's a certain percentage that is berries. And what this Trader Joe's trail mix tries to do is create about the same percentage in each one. So somebody's not getting 75% chocolate, even though that sounds delicious. And so what they do is just try to create a distribution that is about the same for each one. So people are getting, you know, they like that consistency of having about the same in each thing. So there might be, you know, 20 nuts in here and 10 pieces of chocolate and maybe only 5 berries or something like that, because the percentage distribution is the same for each one. So if there's, what is that? 20, 30, you know, 35 or whatever total pieces, they're going to be about the same percentages of each of the treats. Okay, so for the M&Ms, you know, we're trying to see, are we going to fit that claim distribution or not? How far apart are we? So we put our chi-squared star here, chi-squared star, and we write our test statistic. And from the previous pages, our test statistic is always going to be your observed minus your expected squared divided by the expected. So it's going to look like that. But that's just the first one. You have to do one for each category. So that's for blue. And then you would want to do for orange, observed minus expected squared divided by expected. Okay, so you're welcome to pause and come up with the other 4 of these if you want on your own. All right, so I should have it good to go here. Just checking everything. Okay, and then you want to put this into your calculator, and you can put it all together, or you can put it, you know, in pieces. But due to the table, I'm going to take it to 3 decimal places, and you should get 18.777. Okay, 18.777. So that's a pretty large test statistic. I mean, it depends on the distribution because it has to do with the degrees of freedom. But the farther apart these two numbers are, the larger this number is going to be when you square it. And so the larger the test statistic. So you can see that as the numbers are sitting farther apart, it's going to create a larger test statistic. Whereas if those numerator numbers sit very close together, meaning the distributions are very close together, then you're going to end up with a smaller test statistic. So the larger the test statistic, the more your data is saying that you are not fitting the claim distribution. So we're going to use critical region on this one because we can use the table. And so you want to have your chi-squared table out. And your degrees of freedom here are going to be, where are we? Degrees of freedom, we have 6 different colors of the M&Ms minus 1. That's going to give us 5. And then our alpha was not given to us. So because our alpha is not given to us, we're going to assume the 0.05. That's what we always use. It's right in the middle if we're not given anything. And then what we do is we take a look in the table to find our chi-squared. So you look under degrees of freedom being 5. And then you go all the way to the right. So all the way to the right, all the way to the right, because we're only using the right-hand side of the table. And under 0.05, you hopefully can see that we get 11.071. So basically, this number here is the cutoff. So I can just draw it over here on the right side. This is the cutoff. Any number that's larger than this is going to be considered more extreme in terms of our data being happening by chance compared to the null. So, you know, 18.77 is somewhere out here, 18.777. I mean, it's obviously to the right of 11.071. So this is your fail to reject region. It means that the values are close enough together to not be really that odd, whereas out here is your reject H naught. It's the values, it's these large test statistics that are saying these numbers are very different from each other. They do not fit each other. So from that, that's all we need to do. And that tells us that we are going to reject H naught. And so then our conclusion is very similar. There is sufficient sample evidence, because we rejected H naught, sufficient sample evidence to, and then notice our claim, going back to the last slide here, one more, our claim is from the M&M's manufacturer, and the M&M's manufacturer is making the claim on the null that these values are equal. So that's not uncommon for these types of problems to be the claim being the null. So sufficient sample evidence to warrant rejection of the claim that the proportion of each color of M and M's follows the claimed distribution. Now you could say that the proportion of blue is 23% and the proportion of orange is 23% and so on and so forth, but I'm just going to say the proportion of each color of M&Ms follows the claim distribution. So we cannot reject it. We cannot reject the null. So what we have found is that there is in fact enough evidence to reject the null, warrant rejection of the null. We have the evidence to say the null is not valid. We have evidence to support the alternative, that there's more of the different colors in there than what they say. So some of them have more and some of them have less than what they've told us. And we'll do one more example. So we have a company and everything they do is by mail. They want to find out if they're getting approximately the same number of orders on each day of the week. So they take a random sample of 400 orders, just so you know, N is not always 400, but they take a random sample of 400 orders and they observe them. So they take a look at the number of orders. So first thing you want to notice is that here should be observed. These are your observed values. And remember, this is a total of 400. And when we do our expected number, this should also be 400 as well. So you should have the same total, just as a reminder. So in this case, we have 400 orders and we expect them all to be the same. We don't have some sort of claim distribution. So by expecting them all to be the same, we take the 400 and divide by how many categories there are: Monday, Tuesday, Wednesday, Thursday, Friday. And you can see when you do that, you're going to get 80. So if in fact the orders are the same, number of orders every day of the week, you should get 80 orders per day out of 400 orders. So in this case, what we can do is we can say the proportion of the orders for Monday should equal the proportion orders for Tuesday, should equal the proportion of orders for Wednesday, should equal the proportion of orders for Thursday, should equal the proportion of orders for Friday. And then our H1 is at least one of the days' orders is different. Okay. So are these values fairly far apart from one another? That's what we got to see. So now it's time for our test statistic. And notice we have an alpha of 0.025. That is a value that is on our table. So we're able to do a kind of a cool alpha like that. So our test statistic here, just like before, chi-squared star I'll use for my test statistic. So we have observed minus expected squared over expected. We only have 5 of these only, but you can do them if you want. Pause and then come back. I'm just checking. So then you can put this, as you know, into your calculator and see what comes out. And if you do that, you should get 6.75. So again, all together, or you can put them in separately. And then let's take a value from the table so that we can make a decision here. Degrees of freedom is just categories minus 1. There's 5 categories for the days of the week, so we get 4. Our alpha from earlier is 0.025. So we're going to look up our chi-squared. That's going to be whatever value somewhere. Really depends on the degrees of freedom, so it doesn't really matter exactly where you put it, but okay, so degrees of freedom are 4. I'm going to head over to 0.025. I get 11.143. So that's this value here, 11.143. And then you can see that our test statistic 6.75 sits to the left of that. It's somewhere here. 6.75. It doesn't matter. It's not like you know that it's there, and I don't know that it's there either. I just know that it's on the left. And what that tells me is that over here is failed to reject. These are all the different possibilities for values where the numbers are fairly close together. And here is reject H naught over on that side, but that's not what we have. So now we know to fail to reject H naught. So we do not have sufficient sample evidence in this case. There is not sufficient sample evidence to, again, warrant rejection of, and let me go back to show you. So notice the claim is that the orders are evenly distributed, and this is when the orders are evenly distributed. So this is our claim. So very common for these, for the claim to be the null. So warrant rejection of the claim that the orders are evenly distributed over the 5 days of the week. Okay. So if you're wanting to do this on your calculator, you're going to want to go to your lists and put values into observed into one list, expected into another list. Then go to tests. I would scroll up because it's towards the bottom, and it'll want where you put your observed, where you would put your expected, and then your degrees of freedom. And then once you calculate that, it's going to give you what you need. So it'll give you your test statistic, and it will give you a p-value, and arguably the p-value works the same I mean, the idea here between p-value or critical region is that either one works. We use the critical region just because we can take a value from the table, but if a student was to use the p-value method, that's fine. Just make sure that you're telling me that that's what you're doing. But that's all there is for section 11.1.